Suppose you have A1 plus A2 plus A3 plus no infinity, suppose to A20, and we can condense this summation using summation notation like that. You copy this letter. And by the way, this is a Greek letter. It's a capital sigma in Greek alphabet. You copy here A, and you declare one variable que es the index variable. Suppose the frequently variable that we're using is M, or K, or I, or J. This is the most common index variable. Entonces you put it here in the bottom for n equal 1, que es the first. So this one is this one. 2n equal 20. I don't know why. Don't ask me why. Normally, you don't put n equal 20. You put just 20, and that's it. But you need to. This is symbolic, right? Symbolic way to indicate summation, no? Entonces you put here the lower bound, and you put here the upper bound. Okay. Okay. Let's practice a little bit. Twist. This is twist. It's easy. Suppose this example in which you expanding word and power. Suppose summation for k equal 1. K is the index variable to 5 of the one mathematical expression is 1 over k. Okay, we start for 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5. It's the last one. 5 is the last one. That's it. Okay, 1 over 1, if you want, you copy like only 1, no? Not necessarily put 1 over 1. 1 divided by 1 is 1. So 1/2, 1/3 is a fraction. Another example, suppose sigma from k equal 1. No. Let's do in backward now. Backward. Because I give you the summation like that. 1 square plus 2 square plus 3 square plus plus 9 square. And you write this statement like a sigma, o sea, summation notation. Sigma from k equal 1 is the first one, to k equal 9 is the last one of the expression, because the expression is k squared. Because you see any element is squared. You get the idea for the summation notation? Okay.
Yes, sir.
Now let's see the property, the most important property of summation notation. Guys, I promise you can see this in calculus 1. Notation. Okay, the first property is, suppose you have summation from K1 to M. N is 1, N is number 10, 100, whatever. You have inside A sub K, where you multiply everything by constant, C. C represents constant. Belong to the real number. Constant. Entonces si you multiply everything by constant, you put a constant outside, like a common factor. This is logical. Using like a distributive property, you know? It's okay. And when you have a constant, if you want, you put a constant totally outside the game. And when you have, for example, summation, 2 elements, K1 to M to the A sub K plus or minus B sub K. I put plus or minus because maybe it's addition or subtraction, doesn't matter. You can separate, you can split this summation into summation. This is totally logical. Okay, plus or minus, summation, K1 to M to the BK. One more property. We have 1, 2, 3, 4, 5, 6, 7 properties. Okay. Number 3. Well, number 3 is, if you want, you can, suppose you have summation for k equal 1 to m of the h to k. We can, if you want, not necessary, separate into summation. One summation, of course, the same element, ak, no? This summation starting 1, like that, and ending in m. Yeah, I suppose that m is less than m, no? Suppose that this is 100 and this is 50. You separate in two, no? 50-50 or 40-60, whatever you want. So this, the new summation start from m plus 1 to, okay? Sometimes this property we apply not exactly like that. You apply like that. Look, you have, for example, you have summation for k equal m to m of a sub k. Entonces you have formulas to compute the summation when starting 1, but when starting other number we don't. But we break it down like that. You suppose that we starting 1 to the m and subtraction starting 1 to the, this is m plus 1 to the m a sub k. Let's see in some example this, that you can separate. You have 100 elements, you separate in 1640 the summation. This is the idea behind this property. There's no science fiction, it's normal. Okay. Number 4 property is, important. 4, 5, and 6 is when you have summation from k1 to m of the k, the variable is k. Now basically this, you expand it 1 plus 2 plus 3 plus plus n. It's the summation of the first 5 n number and natural number. Well, the formula to compute this, not necessarily addition 1 plus 2, this is crazy. No. The formula is m plus 1 divided by 2. And this is logical because you adding the last and the first is m plus 1. Is this guy. If you adding n minus 1, que is the previous, and 2 is n plus 1 again. And we form here n over 2 couple pairs. That is the reason you multiply by m. For example, you want to add in the first 100 element of the natural number, get 1 plus 2 plus 3 plus 98, 99, 100. It's too stupid doing that way. Look, 1 plus 2 is 3, 3 plus 3 is 6. No. We're doing it that way. Look, 1 plus 100 is 101. 2 plus 99 is 101 again. 3 plus 98 is 101 again. And how many copies? 50. Multiplication by 50. And where come from 50 in the formula? 100 divided by 2. That part. Okay? The multiplication this, by the way, is 5050. In the story. I do in 1 second. And likewise, I doing the summation for the 1 million, 1,000, whatever you want. Okay? Another property, number 5 property. This is a little bit more complicated to understand. Well, you accept que it's the formula, no? And we're using that formula in calculus 1. When you have k squared, k is equal 1 squared plus 2 squared plus to n squared. The formula is m plus 1, and sorry, 2m plus 1 divided by 6. It's the formula when you adding the first n natural number, but a square. It's square. And when there's cubic, is the property number 6, k cubic, okay, 1 cubic plus 2 cubic plus and cubic. The formula is a little bit different. It's similar to the linear. It's n plus 1 over 2 per square, everything. And unbelievable, but true. Okay, this is a property that we are using now. I put some example, but not too much. You cover more example in the review package. Okay. Summation property. Let's see 1, 2, 3 examples to illustrate this property, the application for that property. Okay, example 1, easy. Example 1, easy. Suppose compute sigma k1 to 5 3k. We can expand because the 5, no? Because the 5 is not too big. You see, I put 500, so it's impossible. Well, no, impossible no, but it's too long process, no? And consuming time. So, however, I apply the property to do fast. This 3 as a constant, I put outside the summation. Apply the property number 1. Now, I apply the property number 4, no? I don't remember exactly what is the number. But this is the summation 5 number, que es 1 plus 5. But you no doing like a stupid, like a 1 plus 2. No. You multiply 3 times, and the formula is n plus 1 divided by 2. No? N is 5. N plus 1 is 6 divided by 2. That's it. This is 15. This is 3. This is 45. Final answer. Any question? Do you understand very well? Summation.
Yes.
This is clear. Example 2. For example 2, I have summation from k equal 1 to 20 of the 5k plus 3. Okay, no problem. I understand. I separate in two summation. One summation that contains 5k, and another summation can contain just 3, no? Both summation go from 1 to 20, no? Is the limit. But this is 5, I put a 5 outside, like a common factor. Any common factor you put outside the summation, okay? And this is 3, you put outside if you want. Or not, because, well, okay, entonces, you put outside is nothing, and nothing is 1, no? And nothing is 1. Or you put directly 3 here, whatever you want. Okay, let's solve it one by one. This is easy, this is 5. Entonces, paréntesis, 20. Multiplication by n plus 1, que es 21, divided by 2. And this is 3 times something. 20 times 1 is 20. It's 3 times 20. Do you understand this or no? Because this summation is 1 plus 1 plus 1, 20 times. This is 20. 20 times 3, 23. The answer of this is 1050. The answer of this is 60. The total answer is 1110. Any question? Summation. Okay, one more, and that's it to the review of the summation, because it's too easy. In the review, we practice a little bit more. In the homework online, guys, don't hesitate to ask me any question about the homework online, right? Okay, number 3, example. It's the last one of the summation. Suppose summation from k0 to 14 of the expression k is k squared minus 4. Okay. Okay, this example brings me a new idea. because the formulas that we are studied before start in 1, coño, never in 0. But I don't care because you can, for example, expand a little bit. You plug in 0 here. The 0 squared minus 4 represent A0. And the rest is start 1, 2, 3, 4, 5, and you condense it like that in summation. K equal 1, 14 of K squared minus 4. So at least I know that the first part is -4. And -4, entonces you expand this summation into summation. One summation from K1 to 14 of the K squared, and another summation, minus, because it's subtraction here, look, minus, another summation from K equal 1 to 14 again, of just 4. You want to put a 4 here, or we put a 4 here, and you know there's 1 here. Let's compute that part. -4 is -4. This is the formula for what is the summation for the K squared. The formula is M, pero N es 14, in our summation, M plus 1, que es 15. The formula, let me copy the formula. The formula is N plus 1, 2M plus 1 divided by 6. Este es the formula. So in our example, N is 14, M plus 1 is 15, and 2M plus 1 is 29. No, it's 29 because 2 times 14 is 28, plus 1 is 29, divided by 6. Minus, this is 1, so 4 times 14. 4 times 14. Because this one summation 14 times is 14 multiplication. Okay. The answer is this one. This is -4. This is plus 1015 minus 64. The answer is 950. Any question, guys? No?
No, sir, no question.
Okay, this is easy. Let's move on now to sequence, the most important sequence. We studied last class a little bit fast. What is the idea for the sequence? But we studied 2 important sequences. The first one is arithmetic sequence. Okay, arithmetic sequence. Typical example to explain arithmetic sequence is, suppose this is elementary example, 4, 6, 8, 10, ... This continues forever. But you can see that when you're subtracting this number and the previous, the answer is 2, always. When you're detecting this idea, when the difference D is constant, is arithmetic sequence. And this, I suppose, can continue forever. So the formula of the arithmetic sequence, well, we have 2 formulas, guys. We have the explicit formula, explicit A sub M formula is A sub 1 plus N minus 1 times D. This is the most important formula in the arithmetic sequence. Is the A sub N explicit formula. Let me try to calculate the formula in our specific example 1. This is example 1. Who is A sub 1? A sub 1 is the first, the 4. What is D? D is a common difference. That D is common difference, in our example is 2. Entonces, plus N minus 1 times 2, because D is 2 in our specific example. You leave it like that. Sorry. Let me erase that part. Let me identify. Okay, A sub 1 is 4. And D is 2. Therefore, A sub M, A sub M represents the element in the N position, N arbitrary position. Is A sub 1 que 4, plus n minus 1 multiplication by 2 is the common difference. And you leave it like that, no? Of course, no. You apply a little bit algebra. A sub n is equal 4 plus apply distributive property 2n minus 2. A sub m is equal 4. 4 no. 4 minus 2 is 2. 2n plus 2. No, 4 minus 2 is 2, and 2n is down. So this is the formula that generate any number. For example, for n equal 1 is 4, because 1 here, plugging in 1, 2 plus 2 is 4. Plug n equal 2 is 2 times 2 is 4, plus 2 is 6. And this is the formula that generates. Suppose that I ask you in the test, compute a to 500 element. So you continue the stupid thing, 12, 14, no. You plug it in here. 500 multiplied by 2 is 1,000. 1,000 plus 2, 1,002 is the element 500. Okay? 2 times 500 plus 2. 1,002. This is the arithmetic sequence. What more you have about the arithmetic sequence? Well, no, wait. We have the summation. We have the summation for the arithmetic sequence. Not only determine the element in the specific position. No, not only that. You know, the summation. Suppose I want to add in the element that you add in, for example, A1 plus A2 plus A3 plus A sub m, que you know we can condense in summation notation, no? From n equal 1 to m. But let me put it here, k. K equal 1, k represents the index variable. K increasing 1, 2, 3, 4, 5. N is the last one. Este was the last element. Suppose I want to add in the 500 element in the C, you use 500 here. Of the A sub M, A sub K in this case. You put exactly the same, the index variable. What's the formula? The formula is N over 2 bracket A1 plus A sub M. Okay, this formula give me a similar to the formula that we studied before, but this is more general. Because not necessary. In the other case, the number starts from 1 to any number. So this is not necessarily 1. We start for arbitrary number. Okay? To m. Let me see example for the summation. For example, summation. You suppose you have this arithmetic sequence: 60 plus 64 plus 68 plus 72 plus and you ending in 120. I want to compute this. Okay. Immediately you detecting is or is not arithmetic sequence. You subtract 64 minus 64. 68 minus 64, 4. 72 minus 64. Okay, this is S4. It's the common difference. Nice. Who is A1? 60. A1 is 60. Entonces, I go back to my formula. I have in my hand A1. I have in my hand A sub n. I suppose que the last one. 120. The only information that I need is M. Well, I can expand. It can 1, 2, 3, 4, 5, 6, 7. No. This is stupid. Another more interesting way is using the A sub m formula, explicit formula, this formula. Okay, because I know, okay, let me copy the formula again. A sub m is equal to A sub 1 plus n minus 1 parenthesis d. That's the formula, right? Let me see I copy it right. Yes, I copy it right. Who says sub n is 120? It's the last one. Because I want, okay, I know that n is 1 in this position. N is 2 in this position. N is 3 in this position. N is 4 in this position. But what is n in this case? No idea. A1 is 60 plus n minus 1 and d is 4. Okay, and the only unknown we have is n, exactly the same, the number of the position 120. End the story. So you subtracting 120 minus 60, I move that, divided by 4 is 15, no? All right, 120, 60 divided by 15. 15 is equal n minus 1. Is this. Therefore, n is 16, no? Because 16 minus 1 is 15. Okay, I suppose that this 120 is located in the position 16. And that's it, no? This is just the beginning. Now I'm plugging in my formula. Summation, and this specific arithmetic sequence of the A sub k from n equal 1 to 16, because I know that the ending n 16 is equal, the formula is 16 over 2, n over 2, parentheses, 60 plus 120. 120, 180, multiplication by 8 is 1440. And it's the final answer. Yeah. Okay? Okay, guys. I suppose in the... Let's do one more. Let's do one more. Do you follow me or no? We are totally lost. I know sequence is when the mathematicians speak about what is the easy topic in mathematics, the sequence. Everyone is agreed it's sequence. Because it's just common sense and 2, 3, or 4 stupid formulas. Everything okay, guys? Answer me.
Yes, sir.
Okay. And the rest, good. Okay, super. Okay. I believe you. Let me try another example, another more example, and that's it. Suppose this example. Compute 4 plus 4.5 plus 5 plus 5.5 plus plus 100. Okay, let me investigate if it is or is not arithmetic sequence. Subtraction, 0.5. Subtraction, 0.5. Subtraction, 0.5. I suppose that when I say es que this continue following the same pattern. Entonces, the common difference is 0.5. 1/2. So I need to find m, because remember the formula for the summation sub m, no idea what is m, because I know that n is 1 here, n is 2, n is 3, n is 4, but I don't know what is n here. Entonces, one more time, I apply the a sub n explicit formula. This is 100, I know, it's the last one. This is the first one, 4, n is exactly I am looking for, and d is 0.5. Entonces 100 minus 4 divided by 0.5. The answer is 192, but this is n minus 1. Therefore, n plus 1, o sea, no, 192 plus 2 plus 1 is 193. Okay, entonces I discover that the position for the 100 is 193 in this arithmetic sequence. Now the summation from k equal 1, or n equal 1, whatever, to 193 of this sequence is 193 is m divided by 2, and you adding the first and the last. Entonces the answer is 10,033, 36. Is the answer. Easy or no? Easy or no? Easy or no? Yes. Okay, this is arithmetic sequence. You see in the review package and the test. Now we study now geometric sequence. Geometric sequence. What is the geometric sequence? Let me put an example to explain. Suppose 2, 4, 8, 16, 32, 32, 32, 64, blah, blah, blah. Entonces, when you subtracting, no, doesn't work because 4 minus 2 is 2, pero 8 minus 4 is 4. But when you divide, division, this divided by this, is 2. 4 divided by 2 is 2. 8 divided by 4 is 2. 16 divided by 3 is 2. Oh, everything is 2. So it's division, no subtraction. This is called a common ratio. Common ratio. Common ratio. How do you determine the common ratio? You divide any number in the sequence divided by previous. If the answer is constant, it's geometry sequence. The answer no, it's not geometry. Geometry is special. I promise que en Calculus 2, you see before sequence, but in more detail, deep. This is just the kindergarten part of this. So the common ratio is R. In this case, constant is 2. Therefore, it's geometry sequence. A sub m for the geometry sequence is A sub 1, is the first, R n minus 1. This is the formula in general, no? In particular, for this example, A sub m is equal to A1, so A1 is 2, is the first guy, A1, n equal 1, A1 is 2, and the common ratio is a coincidence, gets 2, it's a coincidence, always is the same, R is 2, I know, n minus 1, and you can condense it, yeah, well, no, you can condense it because this is 2 to the 1 power, addition this is 2 to the, and it's logical, it's true, because when the n is 1, it's 2, when the n is 2, it's 4, 2 to the second power is 4, 2 to the third power is 8, 2 to the fourth power is 16, 2 to the fifth power is 32, 2 to the sixth power is 64. Okay? Super. This is the idea for the geometric sequence. Let's see one example, a little bit more complicated. No, a little bit confusing. For example, you have this sequence 10 divided by 9, comma 9, sorry, comma 81 over 10, comma 729 over 100. And this is for n equal 1, for n equal 2, for n equal 3, for n equal 4, comma. Yeah, I want to investigate what happened at n equal 9. Not too far, 9. I'm missing 5, I'm missing 6, 7, 8, and 9. We can continue with the same pattern, you can. But suppose que it's 900, you are in trouble, no? It's much better doing by systematic way. But no 9, because I want to illustrate the procedure. So the formula is A sub n is equal to A1, que A1 is 10, R n minus 1. Well, first of all, I forgot to say, okay, I want to examine if the series is geometry or not. And you divide this number divided by number, and 9 over 10. Leave it like that or put a fraction, it doesn't matter. You divide this divided by this. 81 over 10 divided by 9. Okay, this is 81 over 10, and this is flipped, is 1 over 9. Simplification, because I know that 81 is 9 times 9. Simplification is 9. Again, we get 9 over 10. Do you see it's the same? I don't want to waste the time, but you trust to me, and when you divide this number divided by this number, it's exactly the same. Now, the common ratio R is 9 over 10. This is the common ratio. Okay? Now, see, you want to find then A sub 9. It's super easy. It's A sub 1. Let me copy the formula. For M, the formula say explicit A sub n formula. A1 R N minus 1. En our specific example, que es 9, es A sub 1, que es 10, paréntesis, the common ratio, que es 9 over 10, raised to the 9 minus 1. 9 minus 1 is 8. Raised to the 8 power. And you put in a calculator, and the answer is a little bit weird. And decimal 4.30467. And you can write in fraction, you can write in decimal. Either way. Now the summation. This is the A sub n to find the position. But the summation is another formula. Suppose I want to add in the element A1 plus A2 plus A sub m. In summation notation is K1 to M or A sub m. Y I suppose that this is geometry, no? Sequence. The formula is A1 is the first. This is the first. Parenthesis 1 minus R n to the n power divided by 1 minus R. This is the formula. Just plug it in. Let me see one elementary example. Suppose this example. 1/2 plus 1 over 4 plus 1 over 8 plus 1 over 2 raised to the n power. Adding this element. This is obvious geometric sequence also. Because the common ratio is 1 over 4 divided by 1/2 is 1 over 4 times 2 over 1 is 2 over 4 is 1/2. And likewise, 1 over 8 divided by 1 over 4 is 1 over 8 times 4 over 1 is 4 over 8, que again is 1/2. Es obvio que the common ratio es 1/2. O sea, little r es 1/2. Es obvio que A sub 1 is 1/2 again. Because it's the first guy. It's a coincidence. Not always happen, but this happened in this example. Entonces, apply the formula. The formula say summation from K1 to N A sub K. When the A sub K is geometric sequence, is the formula say A sub 1, 1 minus R N divided by 1 minus R. In our specific example, A sub 1 is 1/2. This is 1, common ratio is 1/2 again. 1/2 to the raised to the n power divided by 1 minus R is 1 minus 1/2, no? 1 minus 1/2 is 1/2. And 1/2 divided by 1/2 is cancelled. And stay only 1 minus, well, you can apply 1 to the n power divided by 2 to the n power. But I know that 1 to the n power is 1. So 1 minus 1 over 2 to the second power. And this is the formula, no? To compute that. A sub n. Suppose I want to compute for n equal 3. Curiosity. 3 is 1 minus 1 over 2 to the third power. 1 minus 1 over 3 to the third power is 8. So 1 minus 8 is 7 over 8, no? Because I consider that 1 is like a over 8, no? 8 minus 1 is 7. Okay, this is the answer. So in this case, I want to verification. We're doing well because this is easy. Remember, suppose that you adding the 3 first element in this in the sequence is 1/2 plus 1 over 4 plus 1 over 8, and you find least common denominator, que es 8. It's 8. You have 4 over 8 is 1/2 plus 2 over 8 is 1/4 plus 1 over 8 1. When you adding is 4 plus 2 is 6 plus 1 is 7 over 8, exactly the same. We compute using the formula. And this case is easy because we're using only 3 elements, but in this case, suppose we have 500 elements. Oof. It's too long process that we can solve it using only one formula. Okay, okay, okay. Okay. Any question, guys? No?
No, sir.
Okay. Okay. Let me explain now series. Series. What is series? Bueno, series es de summation. Both K equal 1, AK. Pero to infinity. Ooh, infinity here. Like you adding infinity element. Entonces, our intuition is, bueno, professor, si I adding infinity element, the answer is infinity. No, no always is infinity. Let's see one example that is no infinity. Suppose that you adding 1 plus 1/2 plus 1/4 plus 1/8 plus infinity. This continue forever in that direction. You say, no, professor, no, I don't understand. Si you adding infinity element, suppose que es super small element, pero infinity times small, give me infinity. No, I want to prove que no. And after, if you want, we can use the intuition. So the formula is that we're using the same formula. Remember, the formula is A1, 1 minus Rm divided by 1 minus R. Okay, this is the summation. This is the summation when the upper limit is not infinity, it's M. And you separate this in two pieces. A1 over 1 minus R, because I factorization, multiplication, this and this, minus A1 Rm over 1 minus R. Now I want to suppose that M approaches to infinity, a huge number. Okay, this element do not depend on M, stay the same. But this element increasing or decreasing? Increasing or decreasing, depending the R. See R, so R to the N is a power function. See R is a number greater than 1 or equal 1. It's increasing. However, see R is less than 1, or not necessarily less than, absolute value. So positive or negative is less than 1. When you have one fraction number and you raise to the m power, and this m power increasing 2, 3, 4, 5, this number decreasing, approach it to 0. So this is gone, approach it to 0. And this is the formula for the series. Okay. The series is called just S, not H sub M. This is H sub M when it's limited, bounded. But when it's infinity, it's S. Is equal to this under the condition if R, absolute value R, is less than 1. So in the mathematical language, this is called convergent. This series converges to the one specific number. Otherwise, the absolute value R or R is greater than 1, divergent. Divergent means that this summation is equal to infinity. Convergent means that this summation is equal to one number. Okay? Entonces, let's come back to our initial example of the series. It was this, remember? Let me try to use my intuition to understand si this converging or diverging. Geometric interpretation this. Look, suppose we have one segment. This is 0, this is 1, this is 2. The first element is 1. 1. The second element is 1/2. It's 1.5. Or 1.5, whatever you want to put in decimal. Now, 1/4 is 1/4. Here, 1/4. Now, 1/8. 1/8. The next is 1/16. It's a half. 1/32. Do you see que the segment is small, and increase, but not too much? And this converge or diverge? Converge. At what number converge? To 2. So the answer of this summation is 2. But okay, but I want to use in that formula, professor. Because this formula you teach me this formula, no? Summation is equal A1 over 1 minus R. Who is A1 in my problem? A1 is 1. Look at that. The first guy. And what is the common ratio? The common ratio we studied was 1/2, no? Because 1/2 divided by 1 is 1/2. 1/4 divided by 1/2 is 1/2 again. Okay, the common ratio is 1/2. This is 1 minus 1/2. 1 minus 1/2. And 1 minus 1/2 is 1/2. And reciprocal 1/2 is 2, exactly the same. Do you understand very well the idea behind converge or diverge? Converge or diverge? One more example of the series. Series is infinity sum. And I promise que in Calculus 2, we study more detailed series. But the only thing you need to understand in pre-calculus is that the series converge when the series is geometric series and the common ratio is less than 1. And it's equal to that formula, the number that converge. Suppose this example, 2 plus 4 over 3 plus 8 over 9 plus to infinity. This continues forever. Okay. Entonces, fine. So determine, no, first question is determine if this series is convergent or that is geometry or no. Secondly, compute the common ratio. According to the value of the common ratio, you make a decision, convergent or divergent. If it's convergent, then find the number que converge, no? Okay, let me try. To find case geometry, you divide this divided by this. 4 over 3 divided by 2. 2 over 1. No? 4 over 3 times 1/2. 2/3. Let's do it one more. A over 9 divided by 4 over 3. It's A over 9 times 3 over 4. Simplification here is 1, simplification here is 3, simplification here is 1, simplification here is 2. 2/3. Okay. You have no more information about this, but I suppose that indicate it's the same partner, right? So this is geometry. Yes. And the common ratio is 2/3. And 2/3 is less than 1. Therefore, converge. Converge at what value? And this formula. A1 divided by 1 minus R. Who is A1? 2. Who is R? 2/3. 1 minus 2/3. So 2 over 3/3 minus 1/3 is 1/3, no? And 1, this is 3 over 3, no? 3 minus 2 is 1. And flip it that is 6. Yes. This series converges, yes, to 6. Unbelievable, but it's true. Unbelievable, but it's true. Okay. No problem, guys. Let me try in the 20 minutes I have to introduce the new topic. It's a little bit confusing. It's easy, in my opinion, but I don't know why the students don't get the idea. It's about mathematical induction. Mathematical induction. Mathematical induction is one method to prove something. Very effective method to prove something in mathematics. Let me try to present to you a motivation example. And after the theoretical part, and after the example, how you prove that. Suppose okay, we have, for example, the odd numbers. 1. 1 is equal Another odd number is 3. 1 plus 3 is 4. Suppose the next gets 5. 1 plus 3 plus 5 is 9. ¿No? Because it's 8 plus 1. Entonces, en this moment is, wow, I believe, suppose que this is, suppose n equal 1, ¿no? Entonces es 1 square. 1 square is 1. Suppose que this is n equal 2. Entonces 2 square, 4, okay. Now suppose que n equal 3. 3 square que es 9. Oh, it should be true or no? Well, this I make a mistake. Let me try for the next. The next is 1 plus 3 plus 5 plus 7 is equal 16, no? 16 because 9 plus 7 is 16. It's n equal 4. 4 squared is 16. Wow, is it coincidence or is it fact? This is the challenge, guy. How you prove that in mathematics? Because I need to put infinity. No, it's impossible. Consuming time. No. Okay, one more because I am confusing. I try to find the contra example que say que this idea que I believe here is completely false. Entonces, suppose 1 plus 3 plus 5 plus 7 plus 9, no? It's 16 plus 9 is 25. This is for n equal 5. And when you 5 square, is 25. Wow. Entonces, I try, well, okay. I continue 6. No, it's stupid doing that way. And so the problem we have in front of us is 1 plus 3 plus 5 plus plus one of the a sub m, the even number, the odd number. But a sub n of the odd number we studied in the last class, remember, was 2n minus 1. So this is for n equal 1. Look, 2 minus 1 is 1. For n equal 2, 2 times 2 is 4 minus 1 is 3. For n equal 3 is 6 minus 1 is 5. No, this is good. It's a good explicit formula for the a sub n. Is equal n squared. Wow. How you prove that? Well, you prove that using mathematical induction. What is the mathematical induction principle? Mathematical induction principle. Guy, I am recording class or no? Yes. Good. Very good.
Yes.
Okay. Thank you. Principle. Okay. We have 2 steps. The first one, this is just an A. Base step. And the base step, you verification if a statement in 1 is true. What means that? If for n equal 1 is true. That you evaluate for n equal 1 here, 1 square is 1 que es the first one, no? Es when the summation is truncated to the first element. So basically in this problem is 1 is equal 1 square, no? Because it's n equal 1, no? Not always working in the first, maybe in the first is true, is false, but in the second is true and continue forever, true. But this is the basic step. Try to prove the first truth in the sequence. Frequently happen in the first, but not always. And we go to the inductive step. It's the most important and the last step. Okay, the idea behind of the inductive step is you assume arbitrary k in the middle here. K. Arbitrary k. So k is a number in between 1 and m. Suppose que n is 500, no? And k you take like a 100 or 150 or 200. You assume que a sub k is true. Okay. And somehow you need to prove this statement. S sub k is true, imply S sub k plus 1. This statement, complete statement is true. Therefore, if this is true, this is equivalent to say x sub k plus 1. It's also true. Guys, this is a little bit complicated to understand because to understand 100% this principle, you need to know mathematical logic. They say, I don't want to stop explaining mathematical logic, but it's okay, make it sense, you know. If you assume the one guy in the middle is true, and their connection in between this guy you assume is true and the next one is true, now the next is true also, right? And so you prove this. Now this continue forever like a domino piece. You know domino piece? You put a domino piece one beside another piece and you pushing and drop like domino piece. Okay, this continue forever to infinity. So basically, the idea behind is that you assume that this is true, the first one. Entonces now, if x1 is true and imply x2 is true, it's because x2 is true. And it's continuous forever. x2 imply x3 is true and so on. This is the idea behind. Okay. And this is theoretical part, theoretical. And let me see how you implement this idea in the motivation example. So we come back at the beginning. In this example, I want to set up the problem one more time. I try to prove using mathematical induction. It's super powerful method for proof something. Suppose 1 plus 2 plus 3, sorry, plus 5 plus 2m minus 1 equal n squared. This is my problem I want to prove. So I copy here. I want to see in the test the solution like that. Basic step. Basic step is prove that x1 is true. What means x1? N equal 1. N equal 1 is in the right hand side 1 squared. In the left hand side you take the first. Es obvio que 1 is equal 1. It's true. Okay? Si it's not true, entonces violation, entonces it's impossible. And now the inductive step. Inductive step. Okay, you assume one arbitrary k in the middle here. Y I assume que es true. You know, because I am the best mathematician in the world, no? But okay, I know que si you prove like a sequence, this is expand for everyone. Now you prove somehow. How you set out that? Well, you set out like that. 1 plus 3 plus 5 plus ta. But now it's no m, it's k is equal k squared. I assume that this statement is true. So I want to investigate what happened with the a sub k plus 1. It's the next in the sequence. Well, it's 1 plus 2, 3 plus 5 plus 2k plus 1 minus 1, sorry, exactly the same, plus the next. And the next is 2k plus 1 minus 1. Okay, because the only thing I did was replace k plus 1 here in the m to find the expression for the next. And should be equal, n, pero n is k plus 1 squared. I suppose you understand this, yes or no? That the only thing I extending one more element inside the summation. What the next one is k plus 1. How do you get that? Well, in this expression, you plug in k plus 1. In this expression, you plug in k plus 1. Okay. But I know, I assume, remember, it is entire expression is k squared, because I suppose get through this part. I substitution this too long. No, for k squared. Okay, under this assumption. And the other side we have, well, distribute the property 2k plus 2 minus 1. Should be, well, you leave it like that, or you expand this, is k plus 1 times k plus 1, spoiled, is k squared plus 2k plus 1, k squared plus k plus another k, get 2k plus 1. Okay. Now we combine later, k squared plus 2k, 2 minus 1 is 1, positive, and you get exactly the same of this. Just remember the idea. The idea is, you assume a sub k is true. And you prove that a sub k implies that a sub k plus 1 is also true. The conclusion is that a sub k plus 1 is true. And this propagates forever for k plus 2, k plus 3, k to infinity. And you prove when you get the identity, it's the same in both sides. This is the proof of the mathematical. You get the idea or no? Confusing?
No
okay, let's play.
problem.
Yeah. Some problem. Joyce.
Yes, sir.
You got the idea?
Yes, sir.
Okay. Let me try to do one very interesting example. Okay, it's the example. Remember at the beginning, when I studied the property for the summation, we studied this property, and you assume it's true. So 1 plus 2 plus 3 plus plus m is equal m plus 1 divided by 2. Do you remember that? Let me prove that this is true using mathematical induction. Okay? The procedure is x1 is the statement 1, que is at n equal 1. And the left-hand side, we have only 1, que is the first one. And the right-hand side, we have 1 times 1 plus 1 divided by 2. 1 plus 1 is 2, 2 divided by 2 is 1, 1 equal 1. This is the basic step. Now the inductive. Inductive is assume que S sub k is true. S sub k is exactly the same. I copy the original problem, pero I suppose que no m. I suppose que es k. Now I try to investigate what happened with the k plus 1. So k plus 1 is, well, I put 1 plus 2 plus 3 plus plus k. Here I stop exactly the same, plus 1 more, is k plus 1. No? In the right hand side, you replace k for k plus 1. Entonces, k plus 1, and this is k plus 1 is k plus 2, I suppose. Divided by 2, no? But remember the assumption that this guy is exactly the same of this guy. Is equal k plus 1 over 2 plus k plus 1 equal k plus 1 parenthesis k plus 2 divided by 2. Okay, now what should I do? Well, okay, I condensing, no, I condensing this fraction and only one LCD is 2. So we have k plus 1 plus 2k plus 2, no? Distribute the property maybe. K squared plus k plus 3k, no, 2k. Oh, no. 2k plus 2 over 2. Now we have k plus 2k, 3k. K squared plus 3k plus 2 over 2. Okay, I finished the left-hand side. Now I'm moving on to the right-hand side. Well, the right-hand side is easy. You fold it here. K times k squared. 2k plus 1k plus 2 over 2. Combine later, k squared plus 3k plus 2 over 2. And this is exactly the same as this. And you prove this is true using mathematical induction. Okay, guys, enough for today. Too fast, important. Are you clear, everyone? I want to repeat again. Repetition again, because it's important for me and for you. Okay. Now, I am sending the test number 1. You start working with this. Of course, simultaneously, you're working with the lab online, no? The lab online stay, okay? I want to say now. Wait. Say now. Send. I sent. Let me know if you receive or no. And this is the test number 4. And the test number 4 is due December 10 at midnight. And also is due the test number 4 online. Okay? Tuesday will be review package. And the review package, when we finish, we send the final test for the student that need the final test. The student that don't need, no problem. Let me know when you receive. And when you receive, you can leave. I got it. Super. Jonah, you stay with me. Confirmation, guys.
Yeah, no.
You got it?
I have it. Thank you.
Excellent. Perfect. Very good. The student that do not receive for some reason, no problema. You email me, I reply back specific for you.
Got it, Professor. Thank you, sir.
Okay, pleasure. Jonah, I want to drink some water. I right back in 1 second with you. Okay?
Go ahead, man. Take your time.